Okay, so let's start talking about some acids and bases. We are going to first discuss acid-base theory, right? And the first acid-base theory we want to talk about is called Arrhenius acid-base theory, right? In Arrhenius acid-base theory, acids produce hydrogen ions, right, or protons in solution. These are also known as protons in solution, right? So if you have an example like hydrogen chloride gas, right, and you dissolve in water, it produces the proton and chloride ions, right? And if it's just a singular anion, like chloride here, right, singular anions that end in "ide" become ic acids. And since these are singular anions and they become ic acids, you also add for the hydrogen that's there, or the protons are there, right, hydro, right? So in this case, hydrogen chloride makes hydrochloric acid. Some more naming conventions to be aware of too is that if it is a polyatomic ion, usually ends in "ate," then it also becomes an ic acid, but there's no hydro, right? So for example, we have the chlorate polyatomic ion, right? If it's in an acid form, right, with a proton there, it becomes chloric acid. And then if it's a polyatomic ion that ends in "ite," it becomes an us acid. So here, the chlorite ion, polyatomic ion, becomes chlorous acid. Again, no hydro because these are polyatomics, right? You only add the hydro when it's just a singular anion. Just one of these, right? Make sense? Also, when these dissolve in the water, right, they become charged, right? Charged ions, so they are electrolytes. They're sour to the taste, like lemons and limes. They turn blue, litmus paper red, and they also corrode some metals, right? And we've already talked about how they donate ions, like hydrogen protons, right? H plus ions into solution, right? Um, and then we've already talked about the naming. So that's basically what the Arrhenius acid-base theory is about. So here's a list of some common acids, right? You can see the very first one was the example we used, which is hydrochloric acid, HCl, right? Its anion was the singular chloride ion, so that's why we call it hydrochloric acid, right? And notice that all of these, right here, right, all those right there, are singular anions, and they all have hydro in the front, right? The only exception is cyanide, but they all have hydrochloric acid, hydrobromic acid for the bromine ion, hydroiodic acid for the iodine ion, and then the one exception, which is hydro cyanic acid, okay, which has the cyanide ion, right? Then we come down to the ones with a polyatomic. These are all the polyatomic anions, right? Notice none of them have hydro in the front of the name. And we have here the nitrate ion, right? And it became nitric acid. We have the nitrite ion, NO2 minus, and it's nitrous acid. Same here with sulfate, sulfuric acid, sulfite, sulfurous acid, right? Carbonate, carbonic acid, acetate ion is acetic acid, right? Phosphoric acid comes from the phosphate, and then phosphorus acid comes from the phosphite polyatomic ion, right? And so on. So it's important for you to not necessarily remember the names of every single acid there, right? But understand and memorize, or just make sure you understand the naming convention, how we name things. So that's Arrhenius acids. So let's talk about Arrhenius bases. Arrhenius acids donate protons into water, right? But Arrhenius bases donate hydroxide ions, or OH minuses, into water, right? Again, these are electrolytes because when they dissolve in water, the solid, for example, sodium hydroxide, when it dissolves in water, it becomes the charged sodium, positively charged sodium ion and negatively charged hydroxide ion, right? So it's definitely an electrolyte. They feel very slippery and soapy, right? And it can turn, it turns paper, indicator paper, blue, and phenolphthalein pink, right? Phenolphthalein pink. So some typical Arrhenius bases, they're all named something hydroxide because they all have the hydroxide ion, right? But if you have a sodium there, it's a sodium hydroxide. If it's a potassium, potassium hydroxide. If it's barium, barium hydroxide. If it's aluminum, aluminum hydroxide. And that is all about Arrhenius bases. So now comes my favorite acid-base theory, which is the Bronsted-Lowry acid-base theory. The reason why it's my favorite is because my old professor used to call this BLAP. BLAP. Right? For Bronsted-Lowry acid-base theory, right? It always cracked me up because he was a funny guy. Anyway, so according to Bronsted-Lowry acid-base theory, right, an acid is a substance that donates hydrogen ions or protons in solution, right? Which is the same as Arrhenius acid-base theory, but the distinction comes in that a base is a substance that accepts protons, right? So it doesn't have to be a hydroxide ion. Commonly it is a hydroxide ion, but it doesn't have to be a hydroxide ion. So in this example, we have hydrogen chloride gas again, and we add it with water, right? So in this case, the acid, self-explanatory, is the hydrogen chloride, and the base, right, is water, right? And so on the other side of the reaction arrow, we then have water accepting the proton, becoming H3O+, or also known as the hydronium ion, right, and the chloride ion, right? So that's the distinction when it comes to between Arrhenius acid-base theory and Bronsted-Lowry acid-base theory. We get this thing called the hydronium ion, right? Because water can act as a base. We can do this again here with ammonia, which is the base, and water, which is the acid, right? Again, remember that the base is the base is the hydrogen or proton acceptor, and the acid is the proton donor, right? So ammonia being the base, on the other side of the reaction arrows, we get ammonium ion, which is NH4+, because it received a proton from the water, and then we get the hydroxide ion, which gives us a basic solution, right? Gives us a basic solution, right? So that comes with it then new terms we have to remember or learn, right? So up here we have hydrogen fluoride, right? And hydrogen fluoride becomes the fluoride ion over here on the other side of the reaction arrow, which makes the fluoride ion hydrogen fluoride's conjugate base, right? I'm sorry, I wrote over that. That says conjugate base. And then likewise then, since water acts as a base over here, right? And it becomes H3O plus, or the hydronium ion on the other side of the reaction arrow, makes it its conjugate acid, right? And it makes sense too, because this now, since it's the conjugate acid, right, it means it has a proton to donate, right? And it does have a proton to donate because it's the hydronium ion. It's H3O plus. Likewise with the conjugate base, right? It's an it's a fluorine minus, a fluoride ion. It can accept a proton, which is why it's a conjugate base, right? So that's the thing with the Bronsted-Lowry acid-base theory. You've got to remember what your acid is and what your base is, which is always on the left-hand side of the reaction arrow. And then on the right-hand side of the reaction arrow is your conjugate acid and conjugate base, right? So let's try this with a different acid. We have nitric acid here, right? And it's being added to, combined with ammonia, right? So, self-explanatory here, because nitric acid is the acid, right? And if nitric acid is the acid, that means that the other guy on this side of the arrow is the base, which is the ammonia, right? Another trick here too is that the conjugate base of the acid will always be the negatively charged ion. So nitrate here is the conjugate base, con base, right? Let me move my head there so you can actually see what I'm writing. There we go, the conjugate base. And then the positively charged one, it might not always be positive, but usually it is, right, will be the conjugate acid. To the ammonia's base, right? So be sure to be able to identify what is a conjugate acid and what's a conjugate base, and what is an acid and what is a base, okay? So that brings us to talking about the relative strengths of acids. Strong acids are acids that dissociate into ions 100% of the time, right? So they'll give large concentrations of, I'm not sure why that spacing is so weird, but H3O ions, right? H3O plus, or the hydronium ion, right? And it's accompanying anion, right? Large concentrations of both. So in our little example over here, we have hydroiodic acid, or hydrogen iodide, right? It gets dissolved in water and becomes the hydronium ion and the iodine ion. You can see in this graph here then that when it dissociates, 100% of it becomes hydronium and iodine ions, right? And none of it remains as hydrogen iodide, right? So this is just a list of strong acids. A lot of them are binary acids, or acids that have just the hydrogen and one other anion, right? So like hydrogen iodide is a strong acid. Hydrogen bromide, or hydrobromic acid, also a strong acid. Both of those are binary. Hydrochloric acid, another binary acid, and very strong as well. But you also have some polyatomic acids here too, like perchloric acid, and sulfuric acid, and nitric acid, and they are also very strong, right? The next ones are the weak acids, right? Weak acids are ones in which only a few of the molecules actually dissociate. You don't go anywhere near the 100% that the strong acids do, right? Most of it remains as the molecule. For example, hydrofluoric acid here, combining with water, and that should be an arrow. I don't know why it did that, right? Hydrofluoric acid combining with water gives you the hydronium ion plus the fluoride ion, right? But when you look at the dissociation graph here, beginning at 100% hydrogen fluoride and then disassociating into water, most of it actually stays hydrogen fluoride, and we have very little of the fluoride ion and the hydronium ion. So that's a weak acid, right? That's a very weak acid. So weak acids are listed here below, right? So water is a very weak acid. Hydrosulfuric acid from hydrogen sulfide, weak acid, carbonic acid, also weak acid, right? We already talked about hydrogen fluoride. Oh, here's vinegar, acetic acid, also a very weak acid. So all those are weak acids and stuff. So now let's talk about strong bases and weak bases, right? So strong bases are usually formed from group 1 and group 2 metals, right? That includes things that you know, like lithium and sodium, all in group 1, hydroxides. Those are strong bases. Potassium hydroxide is also a strong base. Calcium hydroxide right here from group 2, also a very strong base, right? Why are they strong bases? Well, when they are dissolved in water as a solid, they dissociate completely into their substituent ions of potassium and for KOH, for potassium, into potassium and hydroxide ions, much like strong acids, which completely dissociate into their substituent ions. Strong bases do the same thing. Well, weak bases, very similar to weak acids. They're very weak electrolytes, right? And they produce very few ions in solution. They mostly stay together, right? They mostly stay together instead of becoming their substituent ions. And again, that should be an arrow there. I don't know why it turned into an A with 2 dots ahead of it, on top of it. So an example of a very weak base is ammonium gas combining with water to make ammonia and hydroxide ion, right? This is actually a very reversible reaction because most of it stays as ammonia gas and water. That's why when you smell Windex, you smell ammonia so well, right? Your example there. It's mostly in the gaseous form of ammonia, and there's very little ammonium ion and hydroxide ion, and that's your example of a weak base. So that takes us then to talking about acid-base equilibrium, right? When you have a weak base, you don't have to ever worry about acid-base equilibrium when you're talking about strong bases or strong acids because it's 100% dissociation, right? You only have to worry about acid-base equilibrium when you're talking about weak ones because there's a little bit of the original acid and then there's some of the broken up parts of the acid of the constituent ions, right? So in acid-base equilibrium, we can kind of track the concentrations of each and figure out at what point where there's no more change. It stays at one. There's no more change going back and forth, and it stays at a constant concentration, right? So, in an equilibrium reaction, 2 reactions are taking place, right? There's the forward reaction, right? And then there's the reverse reaction, right? So, in the case of a base, in the case of a weak acid, right? Your forward reaction is, for example, here, hydrogen fluoride combining with water to make fluoride ion and hydronium ion. That's the forward reaction. The reverse reaction is going the other direction, where hydrogen fluoride ions combine with hydronium to make hydrogen fluoride. Fluoride ions combine with the hydronium ion to make back the original hydrogen fluoride and water, and that's the reverse reaction, okay? Once you reach this point called equilibrium, there's no further changes in the concentrations of either the reactants or the products. So in this particular graph here, you see this is the equilibrium, right there, products and reactants, right? And the rate of the forward reaction is actually equal to the rate of the reverse reaction. So as fast as hydrogen fluoride and water become the substituent ions of fluoride and hydronium ion, the fluoride ion and hydronium become hydrogen fluoride and water. right? And that's why you see that this rate here, making products, is the same as the products decomposing back into reactants, right? And once you get to this point right here, which is the equilibrium point, the concentrations of either side, reactants and products, stays the same, right? So acid-base equilibrium leads us to talking about Le Chatelier's principle. Le Chatelier's principle states that when an equilibrium is disturbed, the rates of the forward reaction and the reverse reaction will change to relieve that stress and reestablish equilibrium, right? So one of the ways that we can actually alter the equilibrium or disturb a reaction is by changing the concentrations of either the products or the reactants, right? So when that happens, the rate of the forward reaction and the reverse reaction will no longer be equal. They won't be that same shape that you saw like in the acid-base equilibrium graph that we showed in the previous slide, right? So that means that there's stress placed on the system. So this is just a very simple analogy here. We have tank A, let's say that's the reactants, and tank B, that's the products. And right now, they're in equilibrium, right? Because the tanks are both at equal level. But then when you add more reactants in, right? When you add more reactants in, that disturbs the reaction. That disturbs and stresses out the equilibrium, right? So what's going to happen? The rate of the reaction has to increase so that tank A and tank B are in equilibrium again. And now they are, right? With both of them at the same level. That's basically what Le Chatelier's principle says. So if we want to use hydrofluoric acid, again as an example, we've been using it a lot because it's a very quintessential weak acid, right? Again, remember what I said before. You don't have to worry about equilibrium with strong acids. You only have to worry about equilibrium with weak acids. So let's use hydrofluoric acid as an example again, right? We have hydrogen fluoride combining with water, right? And we get the fluoride ion and the hydronium ion, right? And of course, again, this is a reversible reaction because they're going back and forth between the two and at equilibrium, right? So, given this equilibrium reaction, what happens when we add more HF? This reactant right here. Well, that increases the concentration of the HF. It puts stress on the system that is relieved by increasing the rate of the forward reaction, right? That way, more of the HF is being broken into fluoride ions and hydronium ions, right? So that it can become an equilibrium again, right? Okay, so using that same equilibrium again, what happens when we remove some of the HF, some of the reactant, right? Well, that decreases the concentration of the HF, the hydrogen fluoride. What do you think is going to happen now? Well, that's simple, right? The reverse is going to happen, where the reverse reaction will increase its rate, right? So that more HF is being made, and that balances out the equilibrium. Well, let's see here. So using that same equilibrium again, let's add more product, like some more fluoride ions. Well, that increases the concentration of fluoride ions. How do we relieve it? We relieve it by increasing the rate of the reverse reaction, right? So that there's less hydrogen fluoride because it's being made into HF, reestablishing equilibrium, right? So that's a very basic chemical example of Le Chatelier's principle. All right. So the next slide is actually just a summary slide, right? That describes to you what describes to you the stress that happens that you can inflict onto equilibrium reaction, the change that occurs, and then what you can do to fix it, right? Or the shift, right? So if you add a reactant, right, this increases the forward reaction and it shifts to making more products. If you remove some reactants, it decreases the forward reaction rate. It shifts backwards now to make more reactants to obtain equilibrium again. And then if you add more product, it increases the reverse reaction. It shifts the direction of the reaction towards the reactants. And if you remove product, it decreases the reverse reaction rate, increasing the forward reaction rate, making more products to achieve equilibrium, right? So I would be remiss in my duties if I didn't mention some kind of health or medical application to the Le Chatelier's principle, and we're going to talk about then hypoxia and Le Chatelier's principle, right? So say you're climbing a mountain and you're like 18,000 feet in the air. Well, a person receives actually 29% less oxygen um, when they're that high up in the air. And so they may experience some hypoxia, right? Some signs and symptoms of hypoxia: headaches, increased respiratory rate because you're trying to get more oxygen, right? Increased mental acuity, fatigue, and decreased physical coordination, right? So chemically, what's actually happening? Well, recall that in your blood, hemoglobin is actually what receives the oxygen. So we'll do HB for hemoglobin, AQ, right? And then you plus O2 for oxygen, right? And under normal circumstances, when you're at sea level, there's a nice little equilibrium between making oxyhemoglobin right, and the reverse reaction, which is hemoglobin and oxygen, right? But say you go and climb a mountain and you have 29% less oxygen available to breathe, right? Well, that is this right here, right? That is that condition, that stress. You've removed some of the reactants. Oxygen concentration has gone down. What does that mean then? Well, if the oxygen concentration has gone down, that means it decreases the forward reaction rate, right? So instead of having these nice equal arrows going back and forth, the forward arrow actually becomes much smaller, right? And then the reverse arrow becomes bigger in an attempt to regain equilibrium. What does that mean? That means you're making a lot less oxyhemoglobin, which is what you need to survive, right? And that's why you could experience hypoxia. So, water dissociates as well, right? Water is a weak acid and it can dissociate as well. And so, pure water dissociates into the hydronium ion and the hydroxide ion, right, at 25 degrees Celsius, right? And when it does that, both the concentrations are at 1.0 times 10 to the negative 7 molar. That means you have 1.0, sorry, that means you have 1.0 times 10 to the negative 7 molar hydronium ions, and you have 1.0 times 10 to the 7 molar hydroxide ions, right? And just a quick review here. Remember, when we're doing the Bronsted-Lowry acid-base theory, right, we have a base, which is the water. We have water, which is the acid, right? One of the waters has to be the base, and one of the waters has to be an acid, right? And then so the conjugate base to one water's acid is the hydroxide, and the conjugate acid to one water's base is the hydronium, right? So back to this now, though, because I just mentioned that because I forgot to say it before. But back to this, though. The hydronium concentration is equal to the hydroxide concentration, right? Which is equal to 1.0 times 10 to the negative 7 molar, right? So it's a very special number because if you multiply the concentration of hydronium times the concentration of hydroxide, you get this constant called Kw, right? Kw is equal to the hydronium concentration times the hydroxide concentration. Let's do that math, right? 1.0 times 10 to the negative 7 molar times 1.0 times 10 to the negative 7 molar, and what do you get? You get Kw is equal to 1.0 times 10 to the negative 14 at 25 degrees. That's a very important number right there. Kw is that. It's a very, very important number. You should remember that. So we can use Kw to calculate, right, the concentrations of hydronium and hydroxide ions in different acids, right? So you have Kw equals the product of hydronium ions and hydroxide ions, which you can easily rearrange like we've been doing like with the gas laws, right? Where the hydroxide concentration is equal to Kw divided by hydronium, or the hydronium concentration is equal to Kw divided by the hydroxide concentration, right? We can use them to calculate each other. So let's do that real quick. If I have lemon juice, right, and it's got a concentration of hydronium ions at 2.0 times 10 to negative 3 molar, right? What is the hydroxide concentration of that solution? Well, that's really simple, right? We want to look for this, the hydroxide ion. So OH minus concentration equals Kw over hydronium ion concentration, right? So that means that it's 1.0 times 10 to the negative 14 divided by the hydronium ion concentration, which is 2.0 times 10 to the negative 3, right? And let's just do that on the calculator real quick, just so I can review you guys on how to put in scientific notation. Here we go. Clear. Oops, I didn't press clear, did I? There we go. Clear. Clear. Okay. So I have 1.0 E, so second E, right, to the negative 14. Right? Oops, not 40, 14. Whoops. Right? Divided by 2.0 E to the negative 3. Good. Press enter, and what do we get? We get 5 times 10, 5.0 times 10 times 10 to the negative 12 molar. And that's our concentration of hydroxide ions. Cool stuff. So now that we've established what Kw is, right, and you know that Kw is 1 times 10 to the negative 14, we can talk about the pH scale. This is where the pH scale comes from. So the pH scale is used to indicate the acidity of a solution, right? It ranges from 0 to 14. Why? Because of Kw, right? And an acidic solution are ones that have pHs less than 7. Neutral is at 7. And basic solutions are greater than 7, right? Greater than 7. And I'm sorry, I actually forgot to close down the calculator so we can see this little graphic we have up here, right? So in an acidic solution, right, where the pH is less than 7, what does that really mean? That means that the hydronium ion concentration is less than 1 times 10 to the negative 7. In a neutral solution where pH equals 7, the hydronium ion concentration is equal to 1 times 10 to the negative 7 concentration, right? And then in a basic solution where the pH is greater than 7, the hydronium ion concentration is less than 1 times 10 to the negative 7, right? So this is just a chart over here of like common solutions, acids, and stuff that you would have at home and bases, right? So things like, so here we have at the very top, we have hydrochloric acid right there, right? It's pretty pretty acidic, of course, right? It's got a pH up there at pretty much 0, right? Or down there, I guess, but it's up there in the drawing. Okay, and then so there's a lot of hydrochloric acid actually in your stomach. So that's gastric juices. It's got a pH of 1.6, I think it says. Right? Lemon juice, right there, 2.2 pH. Vinegar, 2.8 pH. Right? Lemon juice is citric acid, by the way, if you didn't realize that. Vinegar is acetic acid. Right? Wow, who would have thought a carbonated beverage like a Coke has an acidity of 3.0 pH, right? It's pretty acidic. More citric acid there with oranges, right? 3.5. Water, of course, pure water right here is at 7, right? We knew that already. We knew that. Drinking water is slightly basic, right? That makes kind of sense because it has like ions in it, right? You don't want to just drink pure water. Boy, do I have a story to tell you guys about that. Blood plasma is a slightly basic as well, right? Oh, I forgot to say milk is slightly acidic. Why do you think it's slightly acidic? Milk is lactic acid. That's why, right? Water. So again, pure water is 7. Drinking water 7.2, slightly basic. Blood plasma slightly basic at 7.4, right? Bile from your liver 8.1. Detergents are between 8 and 9, right? And then bleach, which is sodium hypochlorite, is at 12%. 12 pH. That's pretty basic, right? But the most basic is sodium hydroxide at 14. And I think the common name for sodium hydroxide is lye. Yeah, I think I learned that from watching a cooking show where Alton Brown was making pretzels. I think that's what it was. That's where I learned that lye was sodium hydroxide. You'd think I would know that from being a chemist, but we don't really talk much about common names in chemistry. So let's talk about now how to calculate the pH of a solution, right? It's on a pH is on a logarithmic scale, so pH actually equals the negative log of the hydronium ion concentration, right? Negative log of the hydronium ion concentration. And so, if you have the hydronium ion concentration here, and it's 1.0 times 10 to the negative 2 molar, right? This little graphic down here is just showing you how we take into account our significant figures here. 2 sig figs here, 1 and the 0, right? So to do that over in the pH, the 2 sig figs are going to be the 2 decimal points at the 2 places after the decimal point in the pH, right? So that's how we do that. So let's actually do a quick calculation of the pH of aspirin, right? The pH of aspirin. So aspirin, which its chemical name is actually acetylsalicylic acid, right? I'm really sad that you guys aren't going to be in lab because of social distancing and COVID and all that. Because one of the experiments you get to actually do is actually make aspirin. And don't tell anybody this, but when I was in college and I was in an organic lab and we were making aspirin, I tried my aspirin and I didn't die from it, luckily. Anyway, so aspirin is acetylsalicylic acid, right? And it's an NSAID, a non-steroidal anti-inflammatory drug, right? Kind of like naproxen, Aleve, those kinds of things. Alleviates pain and fever. We all know that, right? And a solution of aspirin has a H3O concentration, right, or hydronium ion concentration of 1.7 times 10 to negative 3. So what is the pH, right? Well, recall that pH is equal to the negative log of the hydronium ion concentration, right? So then we would say then that pH equals negative log of 1.7 times 10 to the negative 3, right? So then what does pH equal? So how do you do a negative log on your calculator? Oh my god, that's so messy. pH equals. Now how do you do a negative log on your calculator, right? So let's look at the calculator real quick. Calculator screen. There we go. So negative log is actually right there, the ln, right? So on, clear, and then there, right? Yeah, there's log right there, and there's negative log. Sorry, there's log, and then there's ln, which is natural log, right? So you want to do log, the regular log, right? So really easy. You do negative log like that, right? And then you just put in the concentration of hydronium, 1.7. Oops, not 17. Can't do those mistypes. Very bad. 1.7, and then E, right, to the negative 3, right? Close the parentheses, and then press enter. And then we get, sorry, I can't see it very well. There we go. So we get negative, so we get pH equals to 2.76955 dot dot dot, right? Lots of numbers right there. So we need to do 2 sig figs, right? Which means that we ended off right there. So pH, oops, pH equals 2.77. So that's a pH, that's the pH of a solution of aspirin that has a hydronium ion concentration of 1.7 times 10 to the negative 3 molar. Pretty simple stuff. So let me close the calculator down real quick here. There we go. So knowing that we can calculate pH using the concentration of hydronium ion concentration, right? We can also go backwards and calculate the hydronium ion concentration from the pH, right? How do we do that? Hydronium ion concentration equals 10 to the negative pH, right? 10 to the negative pH. So let's try that for these examples down here. So we have a pH of 3, right? So we'll start out by saying H3O plus hydronium ion, right, equals 10 to the negative pH, 3, right? Well, this is really simple because when you put that into a calculator, it actually equals 1 times 10 to the negative 3 molar. And that's your concentration of hydronium ions when the pH is 3, right? We'll do the same thing here, H3O plus equals 10 to the negative 3.42. Now that one's not so easy to figure out, right? It doesn't just transfer like that. So let's put this into the calculator. Let's switch over to the calculator view. There we go. Clear. So we want to do 10, right? And this is to the negative exponent, which is going to be this number right here, this x to the minus right there, right? Right there, see? Actually, that's not right, I'm sorry. Let's try that again. 10, right there. Okay, good, 10. And what we want to do is this caret right here, right? Oop, light in the way. There we go, that caret. The caret that's right under the pi symbol, right there, right? The caret to the negative pH 3.42, like that. And that gives us a very long number. Let's change that to scientific notation so that it's more easily readable, right? So second, instead of hit the degree button, which is actually changes from scientific to flow. So we'll change it to scientific. Press enter, and there we go. Gives it to us in scientific notation. And the answer is then, again with two significant figures, 3.80 times 10 to the negative 4 molar. Right? So whenever your calculator spits out that floating decimal that has all those numbers behind it, you know it's kind of hard to tell because there's so many zeros between the decimal point and your actual numbers. Just don't forget to switch it from float to scientific, right? By hitting the second button and the degree button and changing it to scientific notation, right? Cool, easy stuff, easy stuff. So now that we've done all those calculations with acids and with acids and their pHs and such, right? Let's talk about some reactions with acids, right? Acids can react with metals such as potassium, sodium, calcium, magnesium, aluminum, zinc, iron, and tin, right? And when they do, they'll produce hydrogen gas and a salt of that metal that it reacted with, right? So, for example, when the potassium reacts with the hydrochloric acid, you get potassium chloride and hydrogen gas. Or when the zinc reacts with hydrochloric acid, you get zinc chloride and hydrogen gas. Right? Oh, let me turn off the thing here real quick. There we go. Acids also react with carbonates and hydrogen carbonates, right? And when it does, it produces carbon dioxide gas, salt, and water. So hydrochloric acid here can react with solid calcium carbonate, and it gives you carbon dioxide, calcium chloride, and water. Hydrochloric acid also can react with sodium bicarbonate, which is actually the same thing as baking soda, right? And you get carbon dioxide, salt, and water, right? So that's another something else that acids can react with. But I think the most important thing to remember is that acids will participate in a neutralization reaction, right? An acid reacts with a base to form a salt and a water, right? And the salt is formed from the anion of the acid and the cation of the base. So when you combine something like hydrochloric acid with sodium hydroxide, you get sodium chloride and water, which is really interesting because either of these, if consumed, right, are dangerous. Sodium hydroxide and hydrochloric acid, right? Corrosive, dangerous when you touch it, right? But when you combine them with each other, they make salt water, right? Which is just salt water. Very benign. Very interesting stuff. So, when you have a neutralization reaction, you have to be able to balance that neutralization reaction. And so here we have a neutralization reaction that includes magnesium hydroxide and nitric acid. So let's write out these particular molecules, right? Compounds. Magnesium hydroxide is MgOH2, right? Plus nitric acid. Oops, shouldn't be a 2, it should be a 3. There we go. And then that forms, in the neutralization reaction, magnesium hydroxide. Oh, sorry, magnesium nitrate. 2 of those, of course, because magnesium has a +2. Same thing on the other side, too, right? Plus water. So there's your base. There's your acid in the neutralization reaction. And then you make your salt and your water. Right? Classic neutralization reaction. Right? So now we have to balance this because we have only one nitrate here on the left side, but we have 2 nitrates over here. Right? So how do we balance it? It's actually really easy. Right? First thing to do is we have two nitrates over here. So what's the easiest way to get two nitrates over here? Put a coefficient of 2 in front of it, right? Oh no, oh no. Now you have two hydrogens there and two hydrogens there. And you only have, so that's a total of 4 hydrogens on the left side. But you only have 2 over here. So how do you balance that? Well, you add 2 in front of the water, and now you have 4 hydrogens, right? Which also have the added effect of giving you 2 oxygens, which will then balance out the 2 oxygens over there. And it's as easy as that to balance a neutralization reaction. Right. So oftentimes when we're in the laboratory, right, we'll have a bottle of acid of some sort, right, and we have no idea what the concentration is of that acid. So to figure out what the concentration of the acid is, we carried out an experiment called an acid-base titration, right? And in an acid-base titration, we can use something like sodium hydroxide to neutralize a measured volume of acid, right? And the reason why we're able to figure out what the concentration of acid is from the sodium hydroxide concentration is because we can actually measure out how much sodium hydroxide, the solid we have, that we dissolved into the water, right? Which is pretty cool, right? So the way we know that we've actually neutralized the acid, right, making it so that it's 1-for-1 molar sodium hydroxide and acid, right? Or I guess in this case, since it's neutralization reaction, it's salt and water, right? Is we have an indicator in there in the form of phenolphthalein, right? And once things are neutralized, this is the acid at the bottom, the base is in the titrator up there, right? The burette actually is what it's called. It's called a burette, right? And as you drop some base into the acid, right, it turns pink because of the phenolphthalein. And once you get to what we call the endpoint, where things are neutralized, right, we stop dropping the base, and the solution, the neutralized solution, is a very light pink color, right? And that's called the endpoint. That's called the endpoint. So let's do a quick calculation of an unknown acid using titration. What is the molarity of hydrochloric acid if you had 18 mils, 18.5 mils of 2.55 molar sodium hydroxide was required to neutralize 0.01 liters of the hydrochloric acid? So notice the thing that's missing here is this. What is the molarity, the concentration of the acid, right? Luckily, we have the equation of the reaction given to us there. And since it's just sodium hydroxide and sodium hydroxide and hydrochloric acid, it's a 1-to-1 ratio for all of it, right? So we don't have to even worry about balancing it. Lucky us, right? So the easiest way to do this is to do some dimensional analysis, right? And you can do this with data that you recover experimentally as well, right? So it says I dropped 18.5 mils of sodium hydroxide, right? We need to convert that to liters so that we can actually do a molar calculation, right? So I want to get rid of milliliters. So for every 1,000 milliliters of NaOH, I have 1 liter of NaOH, right? And then now I want to be able to convert to molarity, or do a 1-to-1 molar ratio with the molarity of the acid. So for every 1 liter of sodium hydroxide, right? I have 0.225 moles of sodium hydroxide, right? I do that so that I can relate this concentration of sodium hydroxide, right, to the volume I have, right? Okay. Then for every 1 mole, as we see right here, of sodium hydroxide, I have 1 mole of hydrochloric acid right there, right? So we'll do the math, right? 18.5 times 1 times 0.225 times 1, all divided by 1,000. And that gives us 0.00416 moles of HCl. So what was the concentration? Well, we need to divide that by its volume to get its molarity. And luckily for us, it's already in liters. 0.0100 liters. And that gives us a concentration of 0.416 molar HCl. Oops, that's wrong. HCl. And that's how we can use titration to figure out what the concentration is of an unknown acid. And the last thing I want to talk about is buffers. I don't really want to spend too much time talking about buffers, right? But a buffer is a buffer solution, and I told you about buffer solutions earlier when I was talking about keeping proteins and enzymes and DNA and such stable in biochemistry. Well, why do we need that? Because it turns out that proteins and enzymes and stuff like DNA and things that deal with biochemistry are very unstable when it comes to very large changes in pH, right? So how do we mitigate those changes? We mitigate those changes by using a buffer solution, because a buffer solution maintains the pH by neutralizing small amounts of added acid or base, right? An acid must be present to react with any OH added, and a base must be present to react with any hydronium ion that is added, right? So normally when an acid or a base is added straight to water, the pH changes drastically, but in a buffer solution, the pH is maintained, right? When that happens. It doesn't change when an acid or base is added. In fact, it resists pH changes, and you have to add like an overwhelming amount of either acid or base to change it, right? So buffers are normally used to make a buffer. You normally use the conjugate base salt of a weak acid, right? So for example, you can use carbonate, right? So the reason why I bring up carbonate is because, again, I would be remiss in my duties if I didn't mention some kind of health-related thing when it comes to buffer solutions. And your body regulates your blood's pH by using this thing called the carbonate bicarbonate buffering system, right? So you have carbonic acid, right? And you have its conjugate base, which is carbonate, right? And it goes back and forth accepting protons so that your pH stays normal in your blood. And that's the carbonic acid, the bicarbonate, the bicarbonate, carbonate, or maybe it's carbonate bicarbonate buffering system in your blood, right? And that's how your blood resists drastic pH changes, right? So this little graph here just shows you what I was just mentioning here, you can have a pH of 7 for pure water, but if you add even a little bit of acid, it shoots, not just shoot up, but it shoots up the acidity, but it decreases the pH dramatically, right? And vice versa, with adding some hydroxide in there, it dramatically increases the pH and increases the basicity, right? But if you add in a buffer, right? If you had a buffer solution and you added in some acid or some base, you see very little change, right? Very little change. You go from 7 to 6.9 when you add a acid, or you go 7 to 7.1 when you add a base, right? And that is the beauty of buffers. Other buffers too, I already mentioned the carbonate buffering system. You can also use the phosphate buffering system. In fact, most of the buffers that we use in biochemistry are phosphate buffers. There's also tris acetate buffers, all kinds of stuff like that. Anyway, that's going beyond the scope of this class. So that is the last slide.